Hello everyone! Are you ready? It's time for today's bedtime story, Quantum Computing for Babies by Chris Ferry and Worley. This is a ball. It can be red or blue. It is 1 bit of information. 8 bits make a byte. Many bytes make data. Data lives in a computer. Computers are useful. They solve problems. Problems are solved by changing data. Some problems are easy. Some problems are hard. Some problems are too hard for a computer using bits. But wait, what's this down here? It's a quantum bit, a qubit. It can be red or blue or anything at all. Many qubits make quantum data. Quantum data lives in a quantum computer. Data can be copied. Quantum data cannot be copied. We can watch a computer at work, but we cannot watch a quantum computer at work. We can only see the answer it gives. So why do we want a quantum computer? Because quantum computers can solve hard problems. Now you know quantum computing. Thank you for listening to Chronically Online Storytime. Don't forget to like, comment and subscribe. And most important of all, have a good sleep. Night night. Hi, I'm Alice. Welcome to Chronically Online, the show where we look at the history and cultural impact of the internet. Do you enjoy our videos? Do you hate them? I guess the answer is in a state of superposition and will only become apparent if you like, comment and subscribe. If you enjoy our video essays, check out our podcast, The Internet Seriously, which goes out live every Friday at 10:30 a.m. Don't forget to follow us on YouTube, Spotify, Apple Music, and TikTok. So what's the deal with quantum computers? Why are they so complicated? And what is it about them that activates your cryptocurrency-loving colleague with a prominent LinkedIn presence like a sleeper cell, primed with a keyword-focused monologue they've memorized from a finance bro on TikTok and recite word for word, deliberately engineered to make you feel as stupid, confused, and overwhelmed as possible? Every time I've tried to find a video to help me understand a bit more about quantum computing, I feel like I'm actually losing brain cells as I wade through the onslaught of photons, qubits, superpositions, entanglement,
probabilistic output decoherence, advanced encryption standards, Shaw's output factorization, quantum key distribution, guidelines for transition.
There's a small fraction of content creators who I'm going to assume just do it for the rush of feeling more intelligent than the computer science undergrads who have the misfortune of stumbling across their videos in a desperate attempt to pass mathematical processing for applied optics and information. But the rest are enthusiastic nerds who genuinely want the average person to enjoy quantum computers as much as they do. These creators, while well-meaning, are so invested in the particulars that they tend to forget that 99% of people don't care, don't understand, and don't need this much detail. In fact, the information overload frightens away the kind of people who should be researching and legislating the quantum computers that might become relevant to the everyday person in the next 15 to 20 years. Think of it this way. Let's say you'd never seen or heard of a car before and wanted to understand what cars are and how they might impact your life. The more you hear about how the fuel injection system enables the intake valves to compress hydrocarbons which are ignited in order to generate kinetic energy, the more you think, wow, cars are way too complicated for someone like me to understand, I better leave this to the nerds to figure everything out. The problem is, when nerds are left to figure everything out, they focus on their super efficient fuel injection systems and forget to put seatbelts in cars. So today, I want to try and explain quantum computers from a total beginner's perspective, with as little maths as possible, to make you feel more confident to go,
Well, actually, finance bro coworker, you probably won't be able to use quantum entanglement to optimize your crypto portfolio anytime soon.
When people hear the word computer, they think of something smart, powerful, efficient, fast, and useful. When they hear the word quantum, they think, that sounds really impressive and powerful, so a quantum computer must be a super mega powerful, extra fast, extra clever computer, right? Wrong. Let's forget about the quantum bit for a minute. Forget about qubits, forget about entanglement, forget about cats in boxes. Let's think about what a computer actually is. If you don't know already, the invention of quantum computers means that all previous computing is now known as classical computing. And that's what we're going to be thinking about first, before we get anything quantum involved. Explaining what a classical computer does, and more specifically how it works at the big picture level, is tricky because really it depends on what you need the computer for. If you're using the computer to change a 1 into a 0, it uses a NOT logic gate and flips a single switch within its processor. If you're using the computer to hack into a smart fish tank and change the light colour to purple, the computer will be finding an IP address and bypassing security to communicate with another device. If you're using your computer to edit your fantastic video essay, the computation is going to be more like decoding video files, synchronizing audio and rendering effects. So let's forget about these specifics and go more abstract. When I say computer, I'm not talking about a desktop from the 90s. I'm not even focusing specifically on central processing units that perform calculations in your phone or laptop. Instead, we're going to think of a computer or computation more abstractly, like an ancient Greek philosopher with no access to Wi-Fi or even electricity. A computer is a device that takes an input, does something to it, and gives an output. It could be an abacus turning a 0 into a 1, a supercomputer simulating nuclear fusion, or a laptop hacking into a smart fish tank. As long as it does stuff to get other stuff, it's a computer. We use computation in everyday life when we handle the user input, connect to the domain name system, and manage the data needed to send a WhatsApp message or display a picture of baby Yoda made of strontium atoms. But we are also philosophically computing with our brains when we play a game of chess or decide what shape of pasta to cook for dinner. Computation can be digital, mechanical, and even biological. Computers don't need to have graphical displays or even electricity, so long as they do stuff to get other stuff. The very first proto-computers were things like programmable looms, which could process inputs and produce outputs physically without the use of a single wire or circuit. In fact, the earliest analog computer dates back to as early as the 2nd century BC. The Antikythera mechanism would take an input like a date, do some stuff to it, and produce an output like the position of a moon or a planet. So now, if we really gently and calmly bring quantum computers back into the conversation, they are no different from these other abstract ideas or real-world examples. You take an input, you do stuff to it, quantumly this time, and you get an output. Again, the way that the quantum computer works is determined by what you need to use it for. That's not very helpful, is it? I think a problem I experience when I watch a video about quantum computers or even classical computers is that they might explain one specific use case, like how a computer turns a 1 into a 0, but even in the rare cases that I can actually keep up with the maths, I still don't feel satisfied, and I still feel like I don't understand what a quantum computer is. We're going to go into more technical detail for the nerds later in this video essay, but I just want you to know that even if you come away from this with the understanding that a quantum computer is a machine that does stuff to get stuff, that's okay. You don't need to know about entanglement. You don't need to know how a qubit is controlled. In fact, think about the understanding you currently have of your laptop or your phone. Does it really make a difference if you understand that a text is sent by packet-switched network protocols, or whether you think texts are sent by magic? At the moment, we've defined a computer, quantum, classical, or even a human brain as a magic box that does stuff to get stuff. But what's inside the magic box? And what things could we use the magic box to do? Let's think about some practical applications. But wait, you can't just expect me to pretend that quantum computers are magic while you explain cryptography to me. I want to know how they work. I know it's frustrating, but remember, we're thinking about quantum computers like cars. I don't want to get lost in technical details before we've looked at the big picture. Let's deal with cars can drive on roads but you need to wear a seatbelt, and then we can think about how the differential distributes torque from the car engine. The question that we want to answer is this: what's the point of a quantum computer? Why make one? What could it be used for? And how will our lives be different with quantum computers in them? I want to get away from the idea that a quantum computer is like a really extra special supercomputer. In fact, the name computer is quite misleading. They're more like specialised scientific instruments, more akin to the Large Hadron Collider than the phone in your pocket. The Large Hadron Collider isn't better than your phone if you want to send a text, but it is better than your phone at accelerating particles close to the speed of light. Similarly, quantum computers are good at the specific problems we want them to help us with. These are expected to be cryptography, optimization, and simulation. Quantum computers will be good at these things not because they're massive, fast, clever supercomputers, but because they solve problems in a different way to classical computers. Quantum computers can explore many possible potential answers simultaneously and find near optimal solutions to them. Let's take cryptography as an example. Lots of things we do on computers involve secrets, things you wouldn't necessarily want anyone else to know about, like the login details to your bank account, your private messages, your medical records, or your browser history. Encryption is a way to lock away these pieces of information and keep them safe from prying eyes. When something is encrypted, it looks like gibberish to everyone else. If you have the key, you can decrypt the message back into meaningful strings of information. In the digital world, secrets are locked away using maths. That in itself should be enough to deter most people from attempting to steal the information, but for hackers who persist, it is possible to break into these digital vaults if you guess the right key. One traditional type of cryptography, or digital lock, is RSA encryption, named after Rivest, Shamir and Adelman, who came up with the algorithm in 1977. In RSA encryption, you take two huge prime numbers, say 4,294,967,291 and 4,294,967,297, and multiply them together to get 18 quintillion, 446 quadrillion, 744 trillion, 65 billion, 119 million, 617,627. This number, which is 20 digits long, is actually very small compared to the products used in real cryptography, which can be hundreds or even thousands of digits long. RSA encryption is like guarding your digital vault with a riddle-giving wizard who asks,
What two numbers multiply together to get this 20-digit number?
Good luck figuring it out with a calculator. It would take you billions of years to stumble upon the right combination, and that's assuming you could guess a number every second, which you can't. With the help of a classical computer, you might be able to figure out the solution a lot faster, maybe in a few hours or days, guessing millions of combinations a second. But remember, our example of 18 quintillion, 446 quadrillion,
744 trillion, 65 billion, 119 million, 617,627
is very small compared to the kinds of numbers we get in real cryptography. A classical computer, faced with the task of finding every factor of a number that's thousands of digits long, would take longer than the age of the universe. Literally billions or even trillions of years. But an ideal quantum computer, it could solve this problem in minutes. Not because it's more powerful, faster, or better at testing factors than a classical computer, but because of the intrinsic differences between a quantum computer and a classical computer. What are these differences? Okay, fine. It's time to open the magic box. Let's talk about how a quantum computer actually works. I'm going to assume that you have zero knowledge of how quantum computers or classical computers work and start from the very beginning. If we think about what's in our magic computation box, how exactly do we turn our input into useful output with a classical computer? Let's go as simple as possible and get the computer to turn a 0 into a 1. We take our human question, what if this 0 was a 1? and use a programming language like Python, JavaScript or PHP to structure that question using formal logic. The problem is that the computer doesn't even understand these languages directly, so has to further translate them into machine code, a very low-level set of instructions composed of binary. The machine code tells the computer hardware exactly what to do to carry out the request. The smallest piece of computer hardware involved in this process is the transistor, a microscopic switch that can either block a flow of electricity or allow the flow of electricity through. A transistor in the off position represents a 0, and a transistor in the on position represents a 1. We call this on or off, 0 or 1 state a bit, the smallest unit of information in classical computing. So to turn a 0 into a 1, a computer firstly finds the relevant bit from a place stored in its memory. Remember, this 0 bit will be a specific transistor that is off. The computer then flips the bit, turning on the transistor. The voltage goes from a low level, 0, to a high level, 1. This new state, 1, is then stored in the computer's memory, and the computer can retrieve the new bit and print it out if that's part of your request. We did it! We turned a 0 into a 1. It's not very exciting, but this ability to turn 0s into 1s and 1s into 0s, or to keep them as they are, underlies every classical computing task, from sending a WhatsApp message to rendering a 3D animation. Computing is all about automation. If you had to manually flip every transistor needed to hack into a smart fish tank, you would be there for the rest of your life. Automation means we can be lazy and get the computer to do processes for us quickly and automatically. Many transistors come together to make a logic gate, like a NOT gate, and then we can use that to turn our 0 into a 1 with an automatic process. If we want to do something more complex, like write this sentence in a Google Doc, our keystrokes are interpreted by the browser as JavaScript code, which is translated into machine instructions, which tell the CPU to store a character like S in a specific memory location, draw the letter S at a particular pixel on the screen, and save the keystroke to a cache. The CPU stores the instructions temporarily in registers which are built from logic gates, which are built from transistors. Every colour, every letter, and every web address is just another string of 0s and 1s to a computer. They can all be translated from things that humans understand into things that computers understand, and vice versa. A computer doesn't understand this sentence, but it does understand this enormous string of binary. Conversely, the binary string 01000011 is meaningless to a human, but was part of the instruction that told my laptop to print the letter C from the start of this sentence into the script for this video essay. No matter the task, the role of a classical computer is ultimately to turn 0s into 1s and 1s into 0s, or keep them the same. A quantum computer's job is to turn 1s, 0s, and 0-ish, 1-ish numbers into 0s, 1s, and 1-ish, 0-ish numbers. Rather than using transistors, they use qubits. Where it gets confusing is that the way atoms behave at the quantum level is impossible for our human brains to comprehend. Atoms can be in two places at once, tunnel through walls, and maybe even travel in time. Understanding how a quantum computer works means that we have to accept a lot of things that we don't fully understand. Maybe atoms operate in a fourth spatial dimension. Maybe atoms are magic. We don't know. And maybe we will never know. So I'm going to tell you things that sound impossible, and you just have to accept that they're true. Here is a very quick summary of some key concepts in quantum mechanics that are relevant to quantum computing. A superposition. Quantum particles can exist in two positions at once, like a coin being heads and tails at the same time. Entanglement. The state of one particle affects another, no matter how far apart they are. You've got two coins hundreds of miles apart, but when you flip them, they always land on the same side as each other. The observer effect. When we measure a particle, it changes. Our superpositioned coin is in heads and tails at the same time, but when we measure it, it becomes heads or tails. Let's take a similar simple task from classical computing, changing a qubit from a 0 into a 1. Unlike the simple switched-off transistor from classical computing, a qubit is a different entity. It's more like the needle of a 3D compass that can point in any direction rather than just on or off. Changing a qubit from a 0 to a 1 means rotate the compass needle to point in the opposite direction to be a pure 1, or even just somewhere else that isn't 0. A classical computer flips a 0 into a 1 using a NOT gate, and a quantum computer uses the quantum version of a NOT gate, a quantum X gate. This flips the qubit from a 0 to a 1, or from a 1 to a 0. This is like the 3D compass needle flipping by 180 degrees in 3D space, from pointing completely down to pointing completely up. However, qubits can also be in superpositions, like a magical blend of both 0 and 1. So the quantum X gate can also flip those states around. Let's say a qubit has a 60% chance of being measured as a 1 and a 40% chance of being measured as a 0. The quantum X gate flips this, so now the qubit has a 60% chance of being a 0 and a 40% chance of being a 1. So the quantum computer might turn the 0 into a 1, something in between, or even 1 and 0 at the same time. That's great, but like a classical computer, we don't really need to turn zeros into ones. How can we use the qubits at the heart of quantum computers to do something useful? One task that classical computers struggle with is factoring very large numbers, and it's an application that we hope quantum computers will be able to help us with. Let's say we want to find all the prime factors of 6. A classical computer might test every possible number. Can you divide 6 by 6? Can you divide 6 by 5, by 4, by 3, by 2, and by 1? We represent each number in binary so that the computer can use its logic gates and transistors to do the maths for us. So instead of dividing 6 by 2, the computer is actually subtracting 2 from 6 repeatedly until we reach a value less than or equal to 0. So to find the factors of 6, we divide by 6, so we subtract 6 and get 0, so 6 is divisible by 6. We then divide by 5, so we subtract 5 and get 1, and subtract 5 again and get below 0. The remainder is not 0, so 6 is not divisible by 5. We then divide by 4 and 3 and 2 and 1 until we get to 0. We then check whether our factors are prime numbers by finding all the factors of those factors. In the end, the classical computer finds that the prime factors of 6 are 2 and 3. Simple, right? But what if you're trying to find the prime factors of 18 quintillion? Or 17 centillion? That's where things slow down dramatically. The classical computer has to check each factor one at a time. And as the numbers get bigger, the number of bits needed to represent and process all the possible factors increases exponentially. If we have a huge number like the kind of 617-digit number used in RSA encryption, it would take longer than the entire age of the universe to factor it using classical methods, and would require 124 trillion bits. That's a 1 with 308 zeros. This is where quantum computers might be able to help us. Instead of checking every factor separately, qubits can represent and test many possible factors at once in parallel using quantum states. A quantum computer holds all these factors and then does some maths to get the answer. Specifically, it applies the modular exponentiation stage of Shor's algorithm to
all the possibilities at once, and then uses a quantum Fourier transform to detect periodic patterns in the output in order to amplify probability of the correct answer, and measures the qubits in order to collapse the probabilistic state into classical results.
But we don't need to worry about that. A quantum computer is able to amplify the probability of the correct factors, meaning that it could be possible to find answers immediately without having to test every possible combination. At the time of recording, August 2025, the largest number that has been factored by a quantum computer is 21. The quantum computer with the most qubits is IBM's Condor processor with 1,121 superconducting qubits. However, these are still noisy, intermediate-scale quantum computers. They're fragile, error-prone, and run at less than 100 kilohertz. There are some people that believe that quantum computing is completely overhyped, that it's a scientific dead end, or that we're heading for a quantum winter where progress will stall as investment dries up. But then we're in such an early experimental stage, it's impossible to know where quantum computing is headed. Right now we've got the equivalent of classical computers in the 1950s, which were the size of double-decker buses and would crash if a moth flew into the vacuum tubes. Think of the difference even between computers in the 50s versus the 80s, let alone the difference 70 years later. It could take decades to unlock the full potential of quantum computers. The problem is, the moment a cryptographically relevant quantum computer becomes available, all current encryption algorithms will become useless. Perhaps we're erring on the side of caution, but given that it could take years, or even decades, to get quantum-resistant cryptography in place, now is the time to be planning ahead. Better safe than sorry, right? The perception of quantum computing as way too complicated for the layperson to understand is making the whole field very inaccessible. You don't need to be a physicist or a computer scientist to have a bare-bones understanding. You don't even need to know about qubits to grasp that quantum computers are just another kind of machine for processing information. This problem isn't just limited to quantum computing. Anybody who works in STEM is constantly terrified of being outed as an idiot who doesn't know what they're talking about. The desire to be perceived as a respected authority on any topic means that tech policymakers and even senior engineers get lost in the reeds of Schrödinger's cat and quantum entanglement, concepts that are impossible for a human brain to ever fully comprehend. This obsession with specifics means that we're losing the big picture. If quantum computers are going to become part of our lives, we don't have decades to start thinking about post-quantum cryptography. Quantum-resistant algorithms have been developed and even standardized, but uptake is hindered by the perception that it's all too complicated, too abstract, and too far removed from everyday reality. This mindset could delay critical action, and the effects could be disastrous. It will only take one cryptographically relevant quantum computer to expose those private messages, bank accounts, and personal data that needs to be protected. We need more quantum computing for babies, and less obfuscating LinkedIn nonsense. Understanding technical concepts should be a necessity, not a privilege, and simplifying complex ideas is not the same as dumbing them down. It means opening the doors to include everybody. The exclusivity, jargon, and insularity of technology means that power becomes concentrated and fewer voices are included when it comes to developing products, business decisions, and policy making. When knowledge is made accessible and shared with everybody, power is distributed, enabling diverse perspectives, better decisions, and a future that works for all of us. But what do you think? Do you think the fear of not looking knowledgeable enough holds back honest conversations about technology? Should you need a physics degree to make a video essay about quantum computers? Do you think simplifying concepts is important, or does it risk losing critical nuance? And do you think quantum technology is completely overhyped? Let us know what you think in the comments. I've been Alice, and thank you for listening to Chronically Online.